Behind every breakthrough is a simple idea, and casual artificial intelligence reveals the ones that matter. We will focus on what it says about causal and data. Stay with me, the best part is near the end. Chapter 1: Setting the Stage for Causal AI. Why causality is a game-changer. Causal AI in perspective with analytics, analytical sophistication, model scope of services to support causal AI, the value of the hybrid team, the promise of AI, understanding the core concepts of causal AI. Summary note. Chapter 2: Understanding the value of causal AI. Defining causal AI, the origins of causal AI. Why causal AI is the next generation of AI, the business imperative of a causal model, the importance of augmented intelligence, the importance of data, visualization, and frameworks. Getting started with causal AI. Summary notes. Chapter 3: Elements of causal AI. Conceptual models, process models, collaboration between business and analytics professionals, the fundamental building blocks of causal AI models, the elements of visual modeling. Summary notes. Chapter 4: The Future of Causal AI. Where we stand today, foundations of causal AI, the causal AI journey, integrating causal AI and traditional AI. The imperative for managing data, ensembles of data. Generative AI is emerging as a game changer for causal AI, the future of causal discovery. The emergence of causal AI. Reinforcement learning will accelerate model training. Causal AI as a common language between business leaders and data scientists. The emergence of probabilistic programming languages, the predictable model evolution cycle. The emergence of the digital twin, improving the ability to understand ground truth. The development of more sophisticated DAGs, visualizing complex relationships in the DAGs. The merging of causal and traditional AI models. The future of explainability, the evolution of responsible AI. Advances in data security and privacy. Integration will be between models and business applications. Summary. Glossary Appendix. Causal AI tools and libraries. Selected resources. Acknowledgements about the authors. About the contributor index. Copyright dedication. End user license agreement. Chapter 5: Model and Correlation. The core correlation-based AI model begins by identifying raw data. Causal-based AI model, Part 1. A causal AI model models the pros. A sample DAG describes the basic relationships in a model. In Wright's 1921 paper, Correlation and Causation, he used CAUS. A sample DAG illustrating the relationship between stress and heat. DAG with weights illustrated. Chapter 6: Variable and Illustrating. The process of creating a causal AI model is an iterative process. The DAG modified to include price as a treatment. The DAG modified to include a confounding variable. A mediator variable can unlock the relationship between variables. DAG illustrating the chain path type. A DAG illustrating the fork path type. A DAG illustrating the inverted fork path type. A DAG with an unobserved variable. Chapter 7: Causal and Data. DAG for the DDCO Annual Pricing Review and Update Cycle. DAG for the DDCO Semi-Annual Product Review Cycle. Chapter 1: Setting the Stage for Causal AI. The ability to understand information in the context of solving complex problems is not new. From the earliest days of artificial intelligence, scientists and mathematicians have tried to find new ways to understand the world through models and data. The promise of artificial intelligence, AI, is to reach the point where machines could think and provide answers to some of the most challenging problems of our world. There are a huge number of sophisticated analytics tools that provide significant help in understanding what has occurred in the past and predict a possible future from that data. However, one element that has been missing from the analyses is understanding the cause and effect of the observed and unobserved interactions. The dynamic of understanding why events happen and what can be done to change the outcomes is the power and opportunity of causal AI. This chapter will put causal AI in perspective and set the stage for our exploration of the evolution of the field of AI. Why causality is a game changer? Why is there a sudden explosion in interest in causal AI? The answer is both complex and simple. Causal AI enables us to move beyond the predictive modeling capabilities of traditional AI to understand and predict causal relationships between variables in a system. Here are some of the most salient topics that outline the value of causal AI. Understanding causality. Traditional AI models can make predictions based on observed correlations between variables but cannot tell us why a particular outcome occurred. Causal AI, on the other hand, can identify the causal relationships between variables and help us understand why a particular outcome occurred. Causality and understanding the dynamics of causality can be particularly important in fields such as healthcare, where understanding the causal relationships between risk factors and health outcomes can help identify new interventions and treatments. Identifying interventions. Causal AI can help us identify interventions that can change outcomes. For example, causal AI provides a graphical technique to pinpoint the most relevant variables needed to understand specific objective or estimate the consequences of a given intervention. The goal of causal AI is to help an organization assess the possible cause and effects of various policy actions. Causal AI has the potential to enable a team to have a common understanding of a problem so that they can work together to determine why a situation has occurred and establish a plan to arrive at the best next actions. Predicting counterfactuals. Causal AI can predict the effect of a particular variable on an outcome of interest in an alternative scenario. This is especially useful when the variable of interest is not directly observable or measurable, as it allows the estimation of the causal effect on the outcome. For example, it can help predict what would have happened if a particular intervention or policy had not been implemented. Avoiding bias. Traditional AI models can be biased if they are trained on biased data or if they do not account for all relevant variables. Causal AI, on the other hand, can help avoid bias by identifying and accounting for all the relevant variables in a system. This can help ensure that the predictions and decisions made using AI are fair and unbiased. Improving decision-making. Causal AI can help make better decisions by providing a deeper understanding of the causal relationships between variables. This can be particularly useful in fields like business, where understanding the causal relationships between different variables can help businesses make more informed decisions and achieve better outcomes. Causal AI provides us with a deeper understanding of the causal relationships between variables in a system and can help us identify interventions, predict alternative choices and actions, avoid bias, and make better decisions. The next generation of artificial intelligence can benefit from a deeper level of collaboration between data experts, business leaders, and subject matter experts. While AI has long been used to solve complex problems, in this new era of expanded AI, hybrid teams of business and analytics professionals can include an examination of why problems happen and what alternate approaches can help a business move forward to gain a sustainable and measurable advantage when faced with increasingly sophisticated and aggressive competition. Therefore, we are in an interesting and complicated transition in the evolution of artificial intelligence. While the focus of many traditional AI approaches focuses on data and feature engineering, there is a revolutionary trend emerging. Causal AI uses causal inference as the underlying math of cause and effect. The focus of causal AI is on business outcomes. Causal inference is the science of why, as explained so well by Judea Pearl in the Book of Why. The ideal technology causal inference strives to emulate resides within our own minds. Some tens of thousands of years ago, humans began to realize that certain things cause other things and that tinkering with the former can change the latter. While it is time-consuming and challenging to examine all the possible answers, we can easily ask why events happen and what are the primary the cause and effect factors of a problem we are trying to solve. We have many years of experience working with business and technology leaders who are grappling with some of the most complex problems that our current and traditional technologies are designed to solve. We have seen hundreds of emerging technologies come and go that promise to turn human knowledge into packaged solutions that are easy to understand and implement. The history of technology has proven repeatedly that there are no simple solutions to complex problems. However, each technology takes us a step further to addressing issues. For the past 10 years, the focus of AI and advanced analytics has been on analyzing massive amounts of data to understand the answers to difficult problems. Big data was the silver bullet that offered some success but did not go far enough. One of the biggest stumbling blocks to making AI and advanced analytics solutions work effectively is the complexity of the underlying technologies. Typically, business leaders want to be able to visualize the outcomes from the data buried inside applications and from both internal and external data sources. Business managers and leaders want to not only understand what the data tells them about their current situations but what actions they can take to protect and advance their future goals and objectives. Business leaders look to data scientists who employ statistical and computational techniques to determine insights from big data. Many data scientists use correlation and machine learning techniques to identify patterns and anomalies to predict outcomes. Increasingly, business leaders are beginning to understand that there is tremendous potential to leverage AI to solve complex business problems. The greatest potential for AI is to create a way to the complexity from the underlying technology so that data scientists, subject matter experts, data specialists, and business leaders can collaborate to solve business problems. Therefore, one of our goals with this book is to bridge the gap between the data scientist and the business leader so that it opens the door to use the power of causal AI and traditional AI to create a competitive advantage. However, there are no silver bullets or simple answer. Many business and technology leaders are either adopting or evaluating AI-based solutions to automate processes and determine how to improve their businesses. The promise of AI is tantalizing. Organizations can use algorithms to analyze their data in context to anticipate changes in customer requirements and prepare for the future. In competitive markets, it is imperative to be able to understand what and why situations are happening within the business. How can leadership within a business ensure that revenue can grow? When looking into the future, organizations need to be able to understand the impact of the decisions they make. What happens if a product price is reduced by 10%? Will a lower price cause more customers to buy? Will the price increase entice more new customers to buy? If revenue suddenly decreases, does management understand why this has happened and what can be done to change the current course of business? Are customers leaving because of a quality issue triggered because the business began using a new supplier or because of an emerging competitor? Understanding the cause and effect from processes and data is one of the primary reasons why causal AI is emerging as such a critically important approach across the fields of academia and business. The most common techniques that have been used by data scientists are correlation-based techniques that are common in the field of traditional AI. While correlation and causality are related approaches, they are not the same. In brief, correlation is a technique for establishing the statistical relationship between variables. In contrast, causality refers to how one variable has an impact on other variables. In the case of causality, one variable might have a direct impact on a second variable, there could be an indirect effect, or there could be a confounding effect. Causal AI is the art and science of understanding the myriad of relationships between variables that drive relevant causes and effects in a system that we are seeking to understand and manage. Understanding the difference between correlation-based statistical analysis and causality-based analytics is key to being able to employ and deploy the power of causal AI. Therefore, in the next section we will explore the broad area of analytics. Applying a causal AI approach to analytics will help guide organizations to focus on the assumptions and knowledge that we have about how the world works. If we can answer the complex questions about why an issue occurs, we can adapt our approach to solve problems. The goal of causal AI is to be able to understand the story of the data. Causal AI in perspective with analytics is one of the most widely used, and often misused, terms today. The discussion of analytics is widespread. The term analytics often refers to dashboards and historical reports. In addition, analytics includes collections of data, information, applications, and analytical models related to work with descriptive statistics. Analytics encompasses work products resulting from predictive, prescriptive, simulation, and optimization projects and programs. There are many different perceptions and assumptions about what it means to conduct an analytics project. One group may assume a focus on a historical dashboard, while others creating a simulation model might work in the operational area of the business. To make matters worse, there is likely to be a different vision for how to approach analytics. Typically, organizations and departments will be trying to solve very different problems depending both on the problems they need to address and on the stage of their projects. Approaching analytics in the context of causal AI requires a common understanding of the types and approaches to analytics. At a conceptual level, correlation-based AI and causal-based AI approaches have the same roots. They come from the same family/branch/category of advanced analytics. So, before we move forward with our discussion and description of causal AI, let's define the broader term analytics to ensure that we have a common understanding as we move forward in our dialogue. Analytics is one of the most widely used, and often misused, terms today. The discussion of analytics is widespread. Routinely, we talk about analytics with academics, researchers, government officials, university administrators, scientists, business executives, subject matter experts, data scientists, and more. The term analytics is employed when referring to dashboards and historical reports. Also, analytics is used when referring to collections of data, information, applications, and analytical models related to work in and with descriptive statistics. And the term is deployed when referring to work related to and the effort/products resulting from predictive, prescriptive, simulation, and optimization projects and programs. So, it is not surprising to see confused expressions on people's faces when someone talks about analytics. One person is talking about a historical dashboard, while others are trying to convey how a simulation model might work in the same operational area of the business. It can be frustrating for people not to be able to connect on a topic in which they are all deeply interested. We have found that beginning a discussion by defining the analytical maturity model or framework to be used in the ongoing dialogue helps in reducing confusion and ensures that everyone in the conversation has a clearer understanding about what is being said or what others are trying to convey, given the wide range of definitions individuals hold in their minds about the term in areas of analytics. Analytical sophistication model. Various analytical maturity models have been developed, including one by the staff at Gartner. Using an approach similar to Gartner's, we have created an extended sophistication model to clarify and further define analytics enablers, analytics, and advanced analytics. Analytical sophistication model. Analytics enablers. In this model, the initial categories to the left of descriptive statistics, raw data, clean data, standard reports, and ad hoc reports and OLAP, are related to data, dashboards, and historical reporting. These categories are not included in our definition of analytics. These categories are enablers of analytics but not analytics in and of themselves. Analytics begins with descriptive statistics. Analytics, as we are defining the term in this model, extends to and ends at the vertical dotted line encompassing predictive projects. Descriptive statistics provide insights into historical and current data and are valuable and useful tools in analytics projects and work. When an analytics team creates an exploratory data analysis (EDA) to investigate and gain a deeper understanding of a problem space, descriptive statistics play an integral role in examining and outlining how a business scenario operates in the real world and how that operation is described through data. An EDA and the descriptive statistics used provide a view into the factors that are at work and the relationship of those factors. Analytics includes prescriptive projects as well. Organizations begin to experiment with their journey into more sophisticated analytics via prescriptive projects. These projects may illustrate that an organization has an appetite for advanced analytics, and it may show that this type of work is too costly, complicated, and difficult for the organization to embark upon as a sustained activity. Advanced analytics. Beginning at the vertical dotted line in the diagram and continuing to the right, all of the subsequent areas, i.e. predictive programs, prescriptive programs, simulation, and optimization, are encompassed in the category of advanced analytics. For the purposes of our discussion, all of AI, including both families of correlation and causal AI, exists in the portion of the analytical maturity model that is to the right of the vertical dotted line. In our discussion, advanced analytics and AI are synonymous. Scope of services to support causal AI. Causal AI must be viewed as part of the overall computing infrastructure for businesses. Therefore, it needs to be a consideration in the approaches to managing data and cloud services. The hybrid cloud is a critical asset when moving to causal AI. One can argue that analytics can be managed locally. However, in the complex world of advanced analytics and more specifically causal AI, you have to assume that relevant data will come from a variety of sources. Some will be third-party data sources managed in a public or private cloud. Other data may be generated by the Internet of Things, IoT, devices at the edge of the network. Creating a federated data approach that takes into account the fact that there are myriad data sources needed is critical to the success of advanced analytics in the context of causal AI. In any discussion of advanced analytics, the scope of the data is critical to successfully approaching causal AI. For the past decade, data scientists have assumed that if you can collect enough data to create a model, you can make well-informed decisions. However, One of the distinctions between a data-first approach and a model-first approach is the ability to anticipate the type and scope of the data needed to understand relationships between variables and the data that supports establishing causal relationships. Being successful with causal AI requires the ability to discover the relevant data, whether it is internal or external. Some of these data sources may be extremely large, and it would be impractical to move that much data to an internal data center. Some of the early experiments with causal AI have failed because the business simply did not collect enough of the right data to answer why a problem occurred and what approaches will help to understand appropriate next actions. The data that you will need to create a causal AI solution will be varied. For example, there is considerable data that may be stored in data lakes. There will be data from systems of record as well as third-party data sources that are relevant to market trends. In some situations, your organization may have correct information, but there is simply not a large enough corpus of data to make relevant decisions. If an analytics team using a small data set draws conclusions from that data, the answers may be incorrect. Keep in mind that building a causal AI model and solution is an iterative process requiring incrementally adding data that corresponds to variables and relationships modeled. For example, what data might you discover that is relevant to understanding a complex problem? If you were going to try to determine, in an agricultural setting, the optimal time to plant crops, you would need a variety of data ranging from the chemical construct of the soil, the changing weather patterns, and the past planting history. You might also need to understand what crops are selling better in a changing economic environment. If one of these factors is ignored, the resulting analysis will be useless. Data discovery and incrementally adding newly discovered data is critical to building effective causal AI solutions. The hope has been that if we are able to analyze this data, we will be able to understand our world and understand how to transform our businesses. However, harnessing and making sense of data is not simple. As with any emerging technology innovation, moving from the idea of managing data to the reality of discovering solutions to complex problems is harder than anyone could have imagined. There are many practical techniques for analyzing massive amounts of data that has helped organizations in many ways. Tools are available that help bring together many different types of structured and unstructured data to better understand the meaning of information, which has been a tremendous help to businesses. Data warehouses and data marts, for example, have enabled organizations to analyze business data to help make decisions, such as tracking transactions and managing operational data. The value of the hybrid team while taking advantage of a team of professionals when successfully managing a data-focused project is critical to any project. There are requirements when approaching causal AI. We will cover the process of collaboration in a causal AI project in Chapter 5. Many early AI projects have failed when data scientists work in isolation from representatives from different areas of the business. It is particularly important in causal AI to involve subject matter experts very early in the design process. These professionals understand the content and details of the operation that will become instrumental in creating a model that matches the problem as well as having hands-on experience with the most important data sources. Business strategists will help focus the team on the most important business problems that the company needs to address. The promise of AI. While AI was conceived of more than 60 years ago, it has been slow to realize true benefits for industry and business. The promise of artificial intelligence for decades has been the ability of machines to mimic the capacity of the human brain to understand the context of data and make quick decisions even when all the data you need is not available. One aspect of cognition that sets humans apart from machines is that humans typically maintain a mental model of our environment. Creating mental and computing models is one of the key processes to transforming data into a meaningful understanding of phenomena that we seek to explain or understand. A goal of AI is to be able to predict the behavior of individuals. It is no wonder that the best minds in artificial intelligence haven't been able to build reliable and accurate models of similar complexity to those that are inherent in the human brain. It is now possible to develop sophisticated models, deploy those models in a range of operational environments, and treat, integrate, and ingest numerous types of data to produce reliable, scalable, and accurate results. However, none of these approaches go far enough to understand why events happen and how predictions are made. The value of causal AI is that it provides a technique for helping organizations to leverage the power of AI and advanced analytics so that organizations understand why events happen and how to come up with better solutions. Traditionally, AI has been thought of as one large category. However, the reality is that to be successful, there needs to be a more nuanced and multifaceted approach to AI. Commercial firms, regulators, and academic organizations, to name a few, are interested in and eager to work with a new class of AI. This new category of AI needs to provide for transparency in data transformation, model development, and, most importantly, the interpretation of the results produced by AI systems. This is one of the primary reasons why we see that causal AI and causal inference are moving out of research labs and the halls of academia into the commercial market. Almost since the beginning of time, humans have been searching for the reasons why things happen. Once statistics became associated with correlation, there was an effort to disregard the power of causality. However, with the requirement to understand why an event has happened, what it means, and how to change outcomes, causality has emerged as a transformative trend. As we develop a broader and deeper view of causality throughout the book, we will provide definitions and employ a business-oriented use case so that data scientists, subject matter experts, data analysts, managers, and business leaders can have a common vocabulary to understand causal AI and how it is important to implement business solutions that will help the organization move forward. Understanding the core concepts of causal AI as we move through the chapters in this book, we will get into more detail about how causal AI works and the elements that are important to understand. In this next section, we will provide an overview of the key concepts that are required to understand causal AI. Explainability and bias detection. As AI has evolved over the last several decades, models have become more sophisticated, and, in some cases, multiple models are implemented in an analytics pipeline where the models interact and influence the results of the overall pipeline and the individual models. Monitoring and understanding multiple models is challenging and can be difficult to discern the influence of any one model on the overall results or outcomes. In addition to ensembles of models running simultaneously and, in some cases, in parallel, certain analytical techniques in traditional AI rely on algorithms that are very difficult to examine, discern, and understand why certain results or outcomes are produced. Algorithms such as neural networks belong to a class of analytical technical that are referred to as black boxes. These class models have been given this label because the designs of the resulting models and processes running within the models are so complicated that it has been nearly impossible for humans to understand how the input variables are combined to reach the ultimate conclusions. Academics, researchers, and commercial technology companies have been working to develop solutions to provide explainability solutions for neural networks. Over the past 5 years, we have seen solid progress made on providing clear explanations of how neural networks process data and why those models generate the outcomes and results that are seen. It will be a few years before we see and can use explainability technology that will be acceptable to government regulators and governance professionals. A black box model executes its analytical process based on how it interprets the data. The black box model will not be able to provide business managers with an explanation about how the model makes decisions as to why a campaign did not work. As a result, data business managers cannot explain to shareholders or government regulators why certain business decisions were made. This traditional approach to AI lacks two important factors that are imperative for business success: explainability and fairness, or identification of bias. Explainability, it seems logical, and it is mandated by national laws and regulations around the world, that if you are using machine learning techniques to help your organization make decisions based on analyzing data, you should be able to defend the results of your analysis. One of the problems with many approaches to deep learning is that they are built with complex neural networks that have hidden logic that humans find difficult to understand. This becomes a problem when a model is being used to make decisions that impact the fairness of actions taken by an organization, such as decisions about who to hire or when a policy discriminates against a specific group of people. To address this issue, Explainable Artificial Intelligence, XAI, is a set of processes and methods that allows human users to comprehend and trust the results and output created by machine learning algorithms. XAI is used to describe an AI model, its expected impact, and its potential biases. Moving from a black box model to an explainable model requires that the team begin by modeling to define and understand why the problem exists and how it might be addressed. For example, why are we losing customers suddenly? What approach to marketing a product will produce the best results? What is the right dose of a medication for children under the age of 10? When an organization begins by defining the problem, it is much easier to select the variables that are needed to understand a problem before applying data. This method is designed to ensure that a model can be explained and understood. Detecting bias in a model. One of the risks of any technique or approach to modeling that is difficult to examine and explain is that it is difficult to detect and correct for bias. The consequences of these risks can cause an organization to be sanctioned or fined by regulatory authorities and to face a backlash from customers and activists. Bias in data can happen when an organization selects data that has not been reviewed and examined for inherent, historical patterns that may subtly but inadvertently perpetuate past inequities. Bias can creep in when data is selected that is out of step with the problem being addressed or not aligned with the current expectations of management, government regulators, and the public. For example, the data may include information about the age of individuals in the data set that can introduce bias. Therefore, in a black box model, it will be impossible to see that the results are biased against either younger or older individuals. Imagine that a model is used to help an organization select the best candidates to hire for a job. If the model includes data about the candidate's race, age, or sex, the selection process might be inadvertently biased. The collaborative process begins by articulating the problem being addressed before data is added to analyze the business problem being addressed before adding data to the model and analyzing the results. Directed acyclic graphs. A directed acyclic graph, DAG, is the most common type of graphical modeling approach used to illustrate causal relationships between variables in a causal model. In a DAG, a solid forward-facing arrow indicates a subsequent variable is directly affected by the previous variable. DAG provides process guidance as an intuitive way to represent causal relationships between variables. DAG can represent either a direct or indirect effect, which means the sequencing of the model processing through the nodes can move only in a forward direction. There are no recurrent looping cycles. Just as in the real world, time travels only in a forward motion. Let's examine a few examples of how variables impact and interact with each other. In this example of a causal model, one variable is warm weather, a second variable is the consumption of ice cream, and the third variable is drownings. Clearly, people eat more ice cream in warm weather, so there is a direct forward relationship between warm weather and ice cream. Likewise, there is a direct relationship between warm weather and more people drowning because people will swim in warm weather. If, in our causal models, we create a backward relationship or loop that indicates that the variable ice cream is the cause of warm weather, which is clearly wrong and misleading, and impossible, we have created a model that is invalid and is not representative of the real world and the causal relationships that naturally occur in daily life. To continue with our example, if we created a backward loop between the variable of drowning and the variable of ice cream, we would also have created an illogical conclusion. Clearly, this is a simple example that would be obvious to refute. In more complex situations, however, it will take work to understand the complex relationships and causal strengths of relationships between variables. Structural causal model. A structural causal model, SCM, is a type of DAG that is designed as a mathematical framework. Once a DAG is created as a graphical model, the SCM process translates each variable or node into a mathematical equation. For example, in a complex supply chain, the SCM calculates the amount of time required to deliver a part delivered by the supplier to the customer. Therefore, moving from the graphical model of the DAG to the more precise mathematics of the SCM requires a definition of the three common types of variables. These variables include explanatory, outcome, and unobserved. In other words, there are variables that simply explain what a variable is, i.e., a metal component needed by a customer in the manufacturing process. An outcome variable is intended to evaluate the effectiveness of a process defined in the graphical DAG. The outcome variable can be calculated to determine if there is a bottleneck in a process that could impact a supply chain. As the name implies, an unobserved variable is one that is not easily identified in the DAG. For example, it may appear that everything is working well with a supply chain. However, customers are leaving the company. The unobserved variable might be lack of trust in the company or a new competitor who is doing a better job in building customer relationships. SCMs are powerful because they both indicate causal relationships between variables and can make predictions about how these relationships would change if conditions changed. Observed and unobserved variables. An observed variable is a variable that can be directly measured in an experiment, such as the relationship between smoking and lung cancer. If someone has lung cancer, the doctor may ask the patient if they are a smoker. If they are not a smoker, it is likely they have a form of lung cancer that isn't associated with smoking, and the treatment will be different. In contrast, an unobserved variable cannot be seen from observing a patient, for example. There are diseases such as heart disease that can be hereditary. Simply asking a patient about their lifestyle or observing their fitness level would not indicate to the doctor if the patient has underlying risks of getting lung cancer. Counterfactuals. Merriam-Webster defines the term counterfactual as contrary to fact and relating to or expressing what has not happened or is not the case. An example of a counterfactual conditional statement is if kangaroos had no tails, they would topple over. Counterfactuals are the alternate scenarios that are ingested into our causal models. Counterfactuals enable causal models to illustrate the wide range of options and alternate paths that we might want to consider. Therefore, counterfactuals are a core concept in causal AI because they help the team understand what would happen if a situation were different. Counterfactuals refer to a hypothetical scenario where the team can ask questions such as, what would have happened if a causal relationship between two variables didn't exist? For example, what if we had two suppliers of our products rather than one? Would we have had more sales of our new product? Would we have had better customer satisfaction if we had been able to ship products in a week rather than in 3 weeks? In other words, counterfactual analysis would have let us imagine a different outcome. Being able to use statistical and various machine learning algorithms to estimate causal relationships can allow the team to anticipate the impact of change in business models or actions. Confounders in a causal graph. A confounding variable is a variable that influences multiple variables and can lead to a spurious or false association. In a causal AI system, a variable will be classified as either a cause or an effect. A cause, as the name implies, is a variable that directly influences another variable. In contrast, an effect variable is influenced by one or several variables. However, a confounder variable occurs in situations where a variable can be both a causal and an effect. Confounders are extremely important to identify in causal AI and make it difficult to identify the causal relationships between variables. Having a confounder, also called an observed covariate, will likely distort the results of a model and can bias the results of the analysis. A common example would be the fact that lung cancer is caused by smoking and many low-income patients have lung cancer. Would we conclude that having less money means that a patient will have lung cancer? Of course not. However, if you look at this confounder and use it as fact, then you will likely add bias to your modeling. When creating a model, it is imperative to use statistical models such as regression analysis to remove this bias. Colliders. The existence of a collider in a causal AI model often leads to counterintuitive and inaccurate conclusions. Colliders are also known as backdoor paths. A collider is a variable that has pointers to several different variables in a causal diagram or DAG. This causes confusion in understanding the actual relationships between variables. If a variable is not the cause of two conflicting variables, there is a disconnect that can lead to an erroneous conclusion and bias. Therefore, a collider is a variable in the DAG that is impacted by several different variables. These variables are not directly related to each other, therefore, these variables might lead to inaccurate conclusions. If we remember the situation where warm weather leads to an increased consumption of ice cream as well as more drowning deaths, we can't draw the conclusion that ice cream causes people to drown. This would be a collider if we tried to draw a direction relationship between the variable representing ice cream consumption and drowning. Front door and backdoor paths in a causal model. It is important to indicate front door and backdoor paths to understand the cause and effect of a problem. For example, if a company wanted to determine the causal effect of customer satisfaction on sales, a typical question might be: will increasing our customer satisfaction increase our sales? The causal diagram would be drawn. Causal model demonstrating the relationships between product quality, customer satisfaction, and sales. This causal model demonstrates the different types of paths that can exist within a DAG. There is a direct causal relationship between customer satisfaction and sales, which results in a front door path between the two variables. Causal analysis would be straightforward if not for the existence of a backdoor path. Product quality is a common cause of both customer satisfaction and sales, which can be considered a confounder in this specific context. Front door and backdoor paths are sometimes presented in a written format, as shown here. Front door path, customer satisfaction-sales backdoor path. Customer satisfaction product quality-sales. The conclusion that can be drawn from our causal analysis is that to accurately determine the causal effect of customer satisfaction on sales, the company would need to control for product quality as part of their analysis. This would close the backdoor path present in the causal model and eliminate the confounding source. Realistically, it is likely that there would be multiple other variables that would cause both customer satisfaction and sales, such as price, giving rise to more backdoor paths that would need to be closed in a similar fashion. One of the main goals of a DAG is to help identify backdoor paths that confound the relationships between variables. Correlation is the widely accepted statistical method for understanding the relationship between datasets. Typically, correlation assumes that you can use past outcomes to estimate future outcomes. While this may seem logical, there are some fallacies in correlation. The downside of correlation is that it only shows you results based on data but does not explain the cause of the results from that data. Typically, correlation relies on finding patterns and anomalies in data. In theory, this makes perfect sense. By applying analytics of data with machine learning techniques, correlation does a better job of using these patterns to predict outcomes. Causality, on the other hand, is designed to model relationships between a cause and an effect found in data. Unlike correlation, causal AI understands what happens and why. Causal libraries and tools. Causal libraries are software tools packaged to perform key tasks in a causal AI solution. Because these methods are open source, they provide developers with well-designed frameworks to apply methods without having to resort to proprietary approaches. These libraries the complexity for leveraging causal methods such as identifying causal relationships and analyzing and visualizing data. These libraries are very important in creating DAGs. One of the most popular libraries is PyY, which is a Python-based library that includes an abstracted interface to a variety of existing inferences, causal methods. This library was jointly developed by Amazon and Microsoft. There are many other libraries and tools that aid developers in creating solutions. In Chapter 7 we will provide a detailed examination of the tools and libraries available to support causal AI applications. Propensity score. A propensity score is used to reduce bias and the effect of an observed confounding variables. The propensity score is a statistical tool that indicates differences in outcomes based on approaches to problem solving. For example, a propensity score will help understand the effect of different groups of people receiving treatment with a medication based on observed characteristics such as age or medical history. Augmented intelligence and causal AI. As Judea Pearl in the introduction to the Book of Why stated, data does not understand causes and effects, humans do. In the age of computers, this new understanding also brings with it the prospect of amplifying our innate abilities so that we can make better sense of data, be it big or small. The power of causal AI is not just its ability to model and analyze data, but in its approach to augmenting the power of the human brain to understand the world. Despite the speculation about the ability of machines to think, they cannot. While machines are adept at ingesting massive amounts of data, they do not have the essential causal powers of the human brain. The answer to the proposition that machines can mimic and replicate the power of human cognition is augmented intelligence. Only humans can understand the context of data to make intelligent decisions. The ability to model a business problem based on the variables that define it is a human and, more importantly, team process. Could a machine replace the process of modeling a problem and then understanding the counterfactuals that will change outcomes? The only way this would be possible is to have the AI environment ingest all of the data and context needed to understand and solve a problem. Such a machine would be able to anticipate changes and new data needed as circumstances change. In reality, humans have to identify key variables and relationships based on an understanding of the issues. Data specialists must identify sources and determine if they are accurate or biased. In the context of causal AI, augmented intelligence can play an important role in helping humans identify and understand causal relationships. Humans have an ability to understand changes in the world and make decisions based on what they see and experience. It is human to ask the question, what if things were different? Summary causal AI is the implementation of solutions based on causal inference. The power of causality comes from its ability to model a business problem based on the collaboration between team members who understand the business, the data, and the strategy. In this chapter, we provided the foundational information about what is and how it is a critical element to determining how to take actions to improve future outcomes. In many ways, causal AI is not new. Rather, it takes advantage of the foundations of data management innovations over the past decades. It also leverages the tools and services of AI and machine learning techniques. The power of causal AI is that it goes beyond predicting outcomes and instead can identify the underlying causes of an outcome. Augmenting the power of human intuition and knowledge with the overwhelming power of cloud scalability is the benefit of causal AI. Chapter 2: Understanding the Value of Causal AI. One of the purposes of this book is to review the foundational aspects of causal AI and to explore and explain why causal AI is important for business leaders, subject matter experts, data scientists, and analytics professionals to understand the value of this important evolution in the field of AI. While causal AI is a technically sophisticated approach, it will have profound implications for making better business decisions. Causal AI helps managers and leaders understand how to analyze the primary causes of a problem, the effects of those factors on outcomes, and the options available to solve perplexing problems in the most efficient and effective manner possible. In this chapter, we will discuss the principles of causal AI, its origins, and how it has evolved through improvements in infrastructure, networks, languages, data, and analytics. At this stage of development in causal AI, we have the ability to create sophisticated models and methods that can help organizations drive value from large and diverse data sets. This emerging approach is focused on understanding the cause and effect of problems and coming up with ways to transform how businesses can continue to improve outcomes. Defining causal AI. Judea Pearl, the father of causal inference, summed up the power of causality in his seminal book Causality, Models, Reasoning, and Inference. The next revolution will be even more impactful upon realizing that data science is the science of interpreting reality, not of summarizing data. The foundation of causal inference is an intellectual discipline that considers the assumptions, study designs, and estimation strategies that allow researchers to draw causal conclusions based on data. Why is causal AI so important to business? For organizations to be able to understand how to deal with change and uncertainty, they will need the power to understand the cause and effect of business challenges. We believe that causal AI is the beginning of the next revolution in artificial intelligence. Traditional approaches to AI typically involve using data to create models that can perform specific tasks. This approach typically involves using statistical methods and machine learning, ML, to analyze and interpret data. To create models, data scientists train ML algorithms on large sets of data to identify patterns and anomalies to make predictions. The models created by machine learning algorithms are only as good as the quality and relevance of the data used to create the models. If biased data is used or data isn't clean, the model will be inaccurate. In contrast, causal AI begins by defining a problem that needs to be solved. Why is this important? We are at a stage in the evolution of analytics where management teams understand that they need to exploit enormous amounts of data to make better decisions. These managers recognize that they are spending significant amounts of money on their data science and analytics teams. Leaders and managers want to deploy this power to solve business problems so that they can gain a competitive advantage. While much of the focus over the past several years has been on the concept of digital transformation, there isn't a clear understanding of what this means. We believe that causal AI is the key to creating digital transformation for organizations. At the end of the day, businesses want to understand why a problem has occurred, what it means, and what they can do to change outcomes. Achieving these business outcomes requires that teams go beyond traditional AI and traditional analytical approaches. In causal AI, we first focus on creating models that reflect business challenges and then combine those models with relevant data. This contrasts with the statistical-based correlation approach, where AI begins by gathering data to create a model. Once the model is created, the correlation-based approach identifies a subset of data that indicates correlations that exceed the required threshold and then builds and trains models on that data. Causal AI turns the process of model creation on its head. Since causal AI is intended to solve real-world problems, it is important to understand that you first must consider the knowledge that may be either in a database or even in the heads of experts. Depending on the size and complexity of your organization, it may have a formalized knowledge database or a knowledge graph. It is rare to have a greenfield operation with no deep processes and knowledge. One of the most important aspects of causal AI is integrating the critical subject matter understanding into the model. One of the optimal approaches to incorporate this information is to leverage a knowledge graph as a data resource. A knowledge graph is a structural database that stores information about the entities, nodes, and the relationships between them, edges. One of the benefits of a knowledge graph is that it can represent complex information about domains such as finance, manufacturing, healthcare, and agriculture. An example of a knowledge graph might be an airplane manufacturer that purchases components from many suppliers. Each supplier of component parts must adhere to a specification so that when the airplane manufacturer receives these parts, they fit together as intended. Therefore, if your company is that airplane manufacturer and you want to begin to create a causal model, you need to incorporate elements of the knowledge graph into your model. While the knowledge graph gives you an understanding of what you know about your business, it will not enable you to ask causal questions. But leveraging the knowledge graph is imperative so you are not starting from scratch. The goal of a causal AI approach is to be able to understand why a problem has occurred and then to be able to look at potential solutions. In essence, the goal is to understand the cause and effect of a problem. For example, Why are customers not renewing their contracts? While you will be able to take advantage of the data in the knowledge graph to understand how the contracting process works in your company, it will not tell you why there has been a change in customer behavior. Why are product deliveries suddenly taking twice as long as they were only 6 months ago? While each of these questions makes sense, they are not simple. There is a lot of information buried in these questions. For instance, what is the nature of the contracts? Are the existing contracts too complicated for customers to understand? Are competitors changing their contract language so they are simpler compared to your contracts? Do you have data to be able to answer questions about the nature of your contracts with customers? Without sufficient data, you will not be able to answer causal questions. Therefore, it should not be surprising to realize that the causal modeling process will come before ingesting data because you first must understand what data you need to answer complex questions. The most appropriate intervention may be to simplify contract language to encourage customers to renew. However, the intervention may be more complicated. The issue may be related to emerging competitors that are offering more attractive pricing and product quality. This knowledge of the underlying business and technical issues will require the deep insights of the subject matter experts. These experts understand the details of how the business works but also will have insights into variables that are not obvious and therefore cannot be observed. For example, there may be a new federal government regulation that is impacting sales. Subject matter experts will have an understanding of the new regulation and how it could impact the business in the future. The origins of causal AI. The most popular current view and approach to using practical causal inference was developed by Judea Pearl, a developer of Bayesian networks and a professor at UCLA. He is the author of many important books on causality, including the aforementioned Causality, Models, Reasoning, and Inference, and the popular The Book of Why. His many writings define and explain causal inference and demonstrate how this approach provides a more accurate measure of understanding data than traditional statistical analytical methods. Pearl's greatest contribution to causal AI is his development of a modeling framework. In 2011, Pearl won the Turing Award for his fundamental contributions to artificial intelligence. Why causality? Causal inference, as we indicated in Chapter 1, is the foundational AI technology that is used to create AI solutions. Causal inference itself comprises a branch of statistical analysis that extends the capacity of probabilistic reasoning by incorporating elements of hypothesis testing to infer directional relationships between variables. Causal AI, a solution built from causal inference underpinnings, is an AI-based approach that is intended to explain and manage the cause and effect relationships within a business or discipline. Rather than beginning by selecting data sources used to create models, causal AI begins by understanding a business problem by understanding variables that define a problem and how a set of variables impact other variables. You can use causal AI to interpret the solution given the AI machine learning model and the algorithm. The power of causal AI is that it provides a common language for a hybrid team of professionals to collaborate to solve complex problems. Causal AI has its roots in Bayesian networks. Like causal AI, Bayesian networks look to understand relationships between variables. Therefore, it is not surprising that causal AI leverages the core elements of Bayesian networks. In Causality, Models, Reasoning, and Inference, Pearl states, Bayesian networks were developed in the early 1890s to facilitate the tasks of prediction and abduction in artificial intelligence systems. In these tasks, it is necessary to find a coherent interpretation of incoming observations that is consistent with both the observations and the prior information at hand. Bayesian network is a probabilistic statistical graphical that uses quantitative data and is especially useful when there is a limited amount of data on a topic. For example, what is the probability that customers will purchase items primarily from online stores based on available data? A traditional Bayesian model might be used to take a snapshot of 2 years of data and predict that this trend will continue. Causal AI uses a directed Bayesian model because it represents variables as nodes and the causal relationships as directed edges. This model represents the different variables as nodes or points, and the causal relationships between them as directed edges or arrows. Directed Bayesian models are used in causal AI because they are useful in reasoning about complex causal relationships between variables. With causal AI, the team is able to better understand the underlying mechanisms that cause the relationship between variables. However, to understand this data from a causal perspective, it would be important to add more contextual data. History lesson: for centuries people have searched to understand why events happen. Why do people get sick? Why are there floods and famine? Humans are innately driven to understand the causes of these types of events and what they can do to fix problems. Ironically, with all of the technology innovations over the decades, we haven't found a way to clearly express the cause and effect of events. In the 1840s, there was a well-accepted theory called miasma that diseases such as cholera and bubonic plague were caused by pollution, or what was called bad air. Therefore, since the cause of disease was caused by bad air, the cure was to close windows. John Snow, an English physician who had treated many cholera victims, was unconvinced that this theory was correct. Instead, he was convinced that contaminated water was the source of diseases such as cholera. In his essay in 1849, on the mode of communication of cholera, he detailed his theory. Subsequently, he was able to prove his theory during the cholera epidemic of 1854. By talking to residents of a London neighborhood where there was a significant cholera outbreak, he was able to determine that, in fact, the cause of the outbreak was contaminated water. He conducted an experiment. He removed the handle from the pump of the local well, which meant that residents couldn't use the water supply. Snow wrote, "On proceeding to the spot, I found that nearly all the deaths had taken place within a short distance of the Broad Street pump. There were only 10 deaths in houses situated decidedly nearer to another street pump. In 5 of these cases the families of the deceased persons informed me that they always went to the pump in Broad Street, as they preferred the water to that of the pumps which were nearer. In 3 other cases, the deceased were children who went to school near the pump in Broad Street. With regard to the deaths occurring in the locality belonging to the pump, there were 61 instances in which I was informed that the deceased persons used to drink the pump water from Broad Street either constantly or occasionally." Snow was able to definitively illustrate the power of understanding cause and effect. Why tell this story? It is a clear example of why cause and effect is at the heart of how we need to approach decision-making. A replica of the Broad Street water pump. Source: jam/Wikimedia Commons/CC by SA. Expressing relationships, one of Pearl's most important contributions, which turned causal inference from a theory into a practical approach to creating applications, is what is called a structural causal model, SCM. An SMC model basically codifies the ability to express the relationship between the state of a world or situation being addressed and how the available variables related to the data used to explain and iterate on a problem being analyzed. Perl describes an SCM as a set of variables, including the following: explanatory variables, or nodes. An explanatory variable is what you manipulate or observe when changes are applied to a situation. For example, if a student is given a large cup of coffee before an exam, will they do better on the test? It is essentially a response variable. Outcome variables. An outcome variable, also called a dependent variable, is the result of the action of one or more independent variables. For example, if the student drank a large cup of coffee, did their test score improve, and by how much? Unobserved variables. Unobserved variables are those that the developer would not see and therefore are more difficult to account for in the causal model. For example, the student drinks coffee to be more alert during the exam. The unobserved variable is that the temperature in the room is very high and uncomfortable for the student. Therefore, drinking hot coffee in that room may have a negative impact on performance. This unobserved temperature factor can totally change an outcome. The ladder of causation. In addition to the development of the causal model, Perl also provided a three-layer framework for understanding causality. It puts causal inference in context for understanding how to use this powerful concept to solve problems. One of the best ways to understand the meaning and value of causal AI is to understand Perl's framework, inspired by Alan Turing, who proposed to classify a cognitive system in terms of the queries it can answer. In the Book of Why, Perl took this foundation to develop his framework for causal inference, which he called the ladder of causation. The three rungs of the ladder indicate increasing levels of causation from passive forms of observation to the ability to understand and make judgments based on cause and effect from models and data. In brief, the ladder of causation demonstrates how we can move from observing an event to understanding outcomes and then finally to answering the question about why a situation happened. The ladder and, starting from the lowest rung and moving up, its stages: association, the ability to see or observe; intervention, the ability to do or make a change; counterfactuals, the ability to imagine or infer and understand based on observation. The ladder of causation indicates the stages of Perl's view of causality. Rung 1, association, or passive observation. Perl places traditional machine learning methods at the lowest rung of causality because they allow predictions based only on passive observations. At its simplest level, association is about how two observed entities are related. This rung of the ladder relies on observing statistical relationships between variables that are used to train a model. Like Turing, Perl talks about association as the imitation that is prevalent in the way an animal observes the world. Even traditional machine learning depends on imitation rather than learning. The way data elements are related to each other can be inferred directly from observing data using correlation, conditional probabilities, and conditional expectation. Therefore, association is a traditional statistical approach to analyzing data. Rung 2, intervention, or taking action. The intervention rung involves not only passively observing, the tree has green leaves, but understanding the impact of change, why the leaves on the tree have turned. An intervention would begin to answer the question about why a change has happened. Did the leaves on the tree turn brown because the seasons are changing or because the tree has a disease that needs to be addressed? If a tree is diseased, is there a way to treat the problem to return the tree to a healthy state? However, if leaves are falling off the trees because of a seasonal change, there is no need to intervene. Applying interventions to a business situation could be what would happen if the company doubled the price of the product. Will customers continue to purchase the product, or will they look for alternatives that are less expensive? The obvious answer might be, of course, the customers will look for a cheaper product. However, there are more variables and factors that would need to be considered to answer this seemingly simple question. For example, what if all competing products were priced high? What if there were inflationary factors that meant that prices had to be raised so that the company would not go out of business? Could a lack of product inventory lead to a price increase that discouraged customers from buying it? In other words, we have to take into account factors such as economic conditions and customer behavior. To determine this with traditional machine learning, the company would look at statistical correlation from large data sets of customer purchases to decide the answer to the question. While observation and statistical analysis from big data will give us some answers, it will not help us understand the impact of the conditions described in the intervention. Therefore, gaining insights into the situation requires the ability to include changing conditions. This requires creating a causal model that includes variables such as information about the product, such as its components, competitors, supply chain variables, economic conditions of the supply chain, and even details about how customers purchase products. In the real world that we all live in, interventions are something that we do all the time without much thought. For example, why did my headache go away? Perhaps it was because I took a pain reliever or because I ate some food after missing lunch. An intervention helps us to begin to understand the cause of a problem by looking at the cause and effect of making a change, taking the pain reliever or eating food. Since associations are purely observational, they are not model-based. In contrast, an intervention will require a model to understand the context and relationships between variables. With Rung 2, it will be possible to build a model that can indicate the relationship between the observed variables. But in many situations, there simply is not enough information to make a decision that will impact sales. There may be underlying conditions that are not easy to identify that are causing the business problem. Rung 3, counterfactuals, or imagining what if. There is a good reason why counterfactuals are on the top rung in the ladder of causation. A counterfactual is used to determine a hypothesis of what would occur if a new condition were applied to a situation. Counterfactuals are the foundation of establishing causal relationships. The power of Rung 3 is that it incorporates both associations and interventions. Therefore, if we begin by answering counterfactual questions, we can also find the answers to how variables are related from observation and how interventions are understood. The counterfactual approach is the process of imagining what might happen if the facts were different. What if we had priced our product differently than any of our competitors? How would we be able to continue to make a profit? If we first observe that two variables have a relationship, it is possible to begin to understand the context for a problem. For example, if there is a dip in sales and a supply chain issue, are these problems related? There may, in fact, be a correlation between the variables that can be calculated. What if we hire a new supply chain vendor or even several supply chain vendors in various geographical markets? Will that intervention mean that sales will improve? Counterfactuals are an important foundation in many fields ranging from scientific experiments. What would happen if we gave a child an adult dose of a drug? To litigation, what would the jury conclude about whether a defendant was the direct cause of an accident or were there extenuating circumstances, And marketing, why did my marketing campaign fail to generate the expected level of sales? The top rung of the ladder of causality brings us to the notion of what would happen under various conditions. Therefore, imagining is the highest form of reasoning by examining what alternative scenarios would be if conditions were different. This approach gets at the heart of the fundamental question of why. The goal of this counterfactual approach is to articulate the cause and effect of relationships in models and data. Why causal AI is the next generation of AI. Over the decades, there has been a huge amount of progress made in artificial intelligence and machine learning. New algorithms have been developed that enable computer scientists to automate well-defined tasks, even when the underlying data changes. One of the techniques of machine learning is to use sophisticated algorithms that analyze massive amounts of data to create models. Traditional AI is based on the ability to ingest and analyze data using statistical correlation-based algorithms. However, as we will discuss in a subsequent section, it is much harder to predict the behavior of people across markets than one would have thought. This is primarily because AI and machine learning algorithms and models are designed to ingest vast amounts of data to generate the model. Many of these techniques are also used in causal AI. Both deep learning and ground truth are key techniques that are important to understand in the context of causal AI. Deep learning and neural networks typically, data scientists select the data sources that they believe will address the problem. A common approach used by data scientists is deep learning techniques. Deep learning is a subset of machine learning that uses artificial neural networks with multiple layers to learn and make predictions or decisions based on input data. Deep learning can be used to identify causal relationships between variables in complex systems. Deep learning models can be trained to identify patterns in large data sets and make predictions, which can be used to infer causal relationships between variables. However, because deep learning models are typically black boxes, it can be difficult to interpret how the model determined its predictions to understand the underlying causal mechanisms. Neural networks work well in situations where there are large amounts of data and predictable patterns. For example, face recognition is a well-known way that neural networks can be accurate. The model can be trained on millions of images so that the resulting model will know details about a face. In extreme situations, the neural network will be able to identify a specific individual. Neural networks can be used to recognize images in speech, and ground truth is often used to train the network to identify the correct object or spoken word. For example, a neural network can be trained to recognize faces in images, with ground truth data consisting of labeled images that show where the faces are located. Neural networks have been very effective in reading a medical image. The model can be trained to recognize certain conditions such as a suspicious spot on a patient's lung. Overall, neural networks and ground truth are effective when there is a large amount of data available and patterns or relationships in the data can be learned by the network. They are particularly effective in tasks that involve pattern recognition or classification, such as image or speech recognition, natural language processing, and medical diagnosis. However, if data scientists work in isolation from subject matter experts, they may not understand the nuances and complexity of a situation and may not have enough data to solve a problem. In the case of diagnosing an abnormality in a patient's lungs, the model will likely not take into account underlying problems that are specific to the patient and cannot predict the right treatment plan. When there is a well-founded understanding of business data, it is much easier to create a logical model. The concept of collaboration between data scientists and subject matter experts is the core of understanding augmented intelligence, the process of collaboration between humans and machines defined by the hybrid team. Establishing ground truth. Another important requirement for the accuracy of models is establishing ground truth. Ground truth refers to a set of objective and accurate data that serves as a benchmark for evaluating the performance of a model. In causal AI, ground truth consists of what the data science team knows to be accurate. In this way, it provides a way to test and validate the model to see if the model indicates causal relationships. For example, if the organization needs to understand the factors resulting in customer churn for a service, the data engineering and data science teams will collect all relevant factors that may be involved in understanding this problem. Data experts can collect information on pricing, customer service quality, product features, and customer demographics. In this example, the ground truth will be a data set about the current state of customer behavior. This ground truth data now becomes the basis for creating the causal model. In the context of causal AI, ground truth plays a critical role in helping to establish causal relationships. Without accurate and complete ground truth data, it is difficult to identify and validate causal relationships between variables. For example, if an AI system is tasked with identifying the causal relationship between smoking and lung cancer, it will need access to ground truth data on the smoking habits and health outcomes of a large population over time to draw accurate conclusions. The business imperative of a causal model. Although we are talking about causal models as frameworks for the next generation of AI, creating models is something that we do instinctively when we try to figure out solutions to difficult problems. It is common in a business planning session, for example, to go to a whiteboard and plan a new strategy for selling to customers. While this type of brainstorming is useful, to be successful we need to be able to codify processes so that we can execute on the strategy. Causal models are tightly related to augmented intelligence because they bring together all the key constituents that are involved in decision-making to determine the elements of the model. In this way, the team now has a common language for subject matter experts, data scientists, and executives to communicate regarding causal inference. This allows technical teams to better align their applications with the needs of the business and generate demonstrable value. Unlike other approaches to AI, which begin the development process by first analyzing a corpus of data, causal AI applies data only after the model is created. Training causal models with data allow users to quantify relative causal strengths, weights, and the importance of variables. These weightings provide insight into the most important causes relative to a particular outcome, supporting future decision-making. One of the profound benefits of a causal analysis-based approach is that it helps to infer probabilities that an event will occur under conditions that are constantly changing based on new factors, such as a change in market dynamics or the health of a patient. Causal AI is a powerful tool to help hybrid teams understand the business problem being addressed and then creating solutions that help explain why an event happened and how to go about figuring out approaches that will help solve problems. In Chapter 3, we will provide a further discussion of the elements of a causal model. Understanding cause and effect in a marketing campaign. Here, we will provide an example of how causal AI is used to understand the effectiveness of a marketing campaign. Throughout subsequent chapters, we will use this example to demonstrate how causal AI works in the business world. There are many situations where the business needs to understand changes in their markets to understand and then adapt their businesses. One of the most complicated aspects of a business is to find an optimal way to sell products and services to prospects to grow revenue and keep existing customers upgrading to new offerings. Executing effective marketing campaigns are at the heart of business success. But understanding the dynamics of effective marketing is complicated in light of economic and business changes. Take the example of online stores and the changing buying habits of customers. What is the likelihood that customers will excel? That is the heart of casual artificial intelligence. If it helped, a quick subscribe keeps more summaries coming. So how do causal and data connect? That is exactly where we started. Go back to the top and watch it click into place.